Hey guys, today we're taking a look at notes for projectile motion. So taking a look at what that is, define it a little bit, do some application problems, throw some equations at you, and we'll get into some actual applications here. So what is projectile motion? Oh Lord, these are going to be slow animations, aren't they? Okay, good question. Objectives for today, you guys will be able to define what projectile motion is and then distinguish between the different types of projectile motion. I should have also included in here, we do want to be able to calculate some vectors, some different component vectors, and make some predictions based on our formulas. So projectile motion, a projectile in general is just any object that's in motion, so any object that only gravity is affecting it. So we talked about that with free fall last chapter, and the projectile motion is kind of a one broader topic. Free fall is a specific example of a projectile motion, but the object, we're giving it some initial force, some initial push or motion, and then after that initial push, only gravity is affecting our object. We have two dimensions, obviously, with projectile motion. We have a horizontal component and a vertical component. So again, we've got different types of projectile motion. Horizontal projectile motion is just motion rolling on a, motion of a ball rolling along a level surface. That horizontal velocity is always constant. Because again, if gravity is the only thing that's affecting our object, and gravity we know works vertically, there's not going to be any change to our horizontal motion. Now again, here we're thinking in ideals. In real world situations, our horizontal velocity could change based on air resistance or friction and stuff like that. But again, here if we're dealing with ideals, only gravity is affecting that object, so that horizontal motion, that horizontal velocity is not going to be changing. Vertical, again, this is what we were talking about last chapter with free fall, motion of a freely falling object. The force due to gravity is the thing that's pulling down on it. That's going to change that that's going to cause that acceleration of our object. And in this case, again, our vertical component of velocity changes with time because we have gravity acting on it. So that force due to gravity is accelerating the object downward. So we are going to have a change in our velocity vertically. And then we also have parabolic path, which is combining those two different things together. So the path that when we have both horizontal and vertical motion happening of our object, it creates this path that ends up being a parabola based on the acceleration. Because the way that this works, and I've got this nice little animation here that kind of shows this. So we see that the gravity-free path, so that horizontal motion, again, we have set spaces in between, right? That horizontal motion stays constant throughout. But as you look vertically, a ball in free fall would be falling with bigger spaces in between each time interval because it's accelerating as you go down, right? It's speeding up as you go, as you continue to fall. So that means as you get further down here, because it's starting to go faster, there's going to be more space in between those spaces, in between those time intervals. So if you followed both a constant horizontal velocity and then a changing vertical velocity, it actually creates this parabola. Which, if you look back and think about our parabola shortcuts that I taught you guys back in Algebra 1, and for those of you who are still in Algebra 2, that 1, 3, 5 shortcut, remember when we were doing our graphs for our parabolas, that horizontal space was always consistent, right? We went up 1 over 1, up 3 over 1, up 5 over 1. That horizontal component to that parabola was always over 1 because that horizontal velocity in this case stays consistent. It's the same interval in between each one. But that vertical velocity, as you continue to fall, gets bigger and bigger and bigger, which was that 1, 3, 5 aspect of the shortcut. So connection to stuff we've done before. So that's how we get that parabolic path. So anytime you throw something, launch something, shoot something off, where you're giving it an initial velocity, initial push, kick, launch, throw, whatever it is, ignition, and then after you do that launch, it's just under the power of gravity. It's not self-powered at all. It's going to follow this parabolic path. All right, so some examples of projectile motion here. We've got a cannonball launching. Now this one, the one thing that we're going to have to be kind of careful of and adjust for and take account of is when we have a variety of heights. So here, this is again just showing these are just at different time intervals what our different velocities are horizontally and vertically. So here, notice my notation, v sub x, that is my velocity in the horizontal direction, right? X being our horizontal, y being our vertical components. So v sub x is my horizontal velocity. And you notice here, after that cannonball has been launched, I have a consistent just 20 meters per second all the way throughout my motion here. But my vertical velocity, my vy, is changing. Here we approximated, just to make it nice clean numbers, negative 9.8, which here obviously they're just approximating to negative 10. We're seeing that every second my vertical velocity is going to be decreasing 10 meters per second because of that acceleration of gravity. So you can see my vertical component vector for my velocity gets bigger as time goes on. Here's just an animation of what it would look like, kind of the same idea, but just in motion. And here, launching it at an angle instead of just launching it straight horizontally. So now we're launching that projectile up and out as well. So you can see, again, this kind of changes as time goes on. My horizontal velocity stays consistent at just 60 meters per second all the way throughout. My vertical velocity, you can see, initially, because I'm going up, starts off positive. Once it reaches its peak and then starts falling down, that velocity becomes negative. But again, you see every second that goes by, you're decreasing by about 10 meters per second. All right, so this is going to be a very, very important slide for us here. This has all of our equations. I'll also probably turn this into a little cheat sheet and post it somewhere for you. But for sure, once I'm done going through this, you probably want to pause your video just to go through and make sure everything is written down here, because these are our equations that we'll use. So our equation for our x component. So this is, in this case, since we just have x for our component thing, it's just talking about the distances. So this is my horizontal distance based on a bunch of information. So x sub f, this is our final horizontal distance. The way we get that is we take our initial horizontal distance, so that's x sub I, plus our initial our initial horizontal velocity, v sub xi, or ix sometimes. That's just that initial horizontal velocity times how long we're traveling in that direction. So again, that kind of makes sense. We're looking at it in terms of distance formulas. It's our rate times our time plus any initial spot that we started at. For our vertical component, it's a little bit different because here we have to account for gravity. Whoops, going back. So here for our horizontal component, or sorry, vertical component, this is the position of, like the height position. My final height is based on my initial height plus my velocity, my vertical velocity initially times time, so that same thing. But here, because we're having that acceleration happening, we have to take this into account. So we also have to subtract off minus 1/2 gt squared. So that's our formula for the vertical position. I have a formula for my vertical velocity. So my final vertical velocity is equal to my initial vertical velocity minus gravity times time. And then my last two here, my different vectors, this is how we take into account our angle that we're happening at. So here, our vertical and our horizontal initial velocities, Vxi, is equal to our initial velocity, that's just of the projectile, times cosine of the angle that it's projected at, that's launched at. And then my vertical component vector, my initial vertical velocity, is equal to, again, that initial velocity of the projectile itself times cosine of that angle. All right, so factors affecting projectile motion, like we said, these are where those numbers come from. So of our actual projectile, not our horizontal component or our vertical component, but the actual initial velocity of the projectile itself, that's v sub I, that's my initial velocity. And then the angle that it's launched at is always based on the angle from the horizon. So however many degrees I am above horizontal. So in this case, here, I would say that's probably about maybe a little bit more than 60 degrees, 70 degrees-ish for my initial velocity, or my initial angle. And then here, my initial velocity, 60 meters per second, I could use those two things to figure out my initial vertical and my initial horizontal velocities. All right, so we're gonna do a little application here. And then on Tuesday, just so you guys know, Tuesday we'll be doing some more practice problems with these, so you guys can get a little more better acquainted with some projectile motion problems. But just to go through one together. So in this case, we have an object that's fired from the ground at 100 meters per second at an angle of 30 degrees with the horizontal. Or I guess in this case, I probably should have phrased this as from the horizontal, from the horizon. So that means 100 is our VI, that's our initial velocity. 30 degrees would be that angle, would be theta. So for part A, we're asked to calculate the horizontal and the vertical components of that initial velocity. So the initial vertical velocity and the initial horizontal velocity are those two things. So the way that I would do that, here are my formulas. So my initial horizontal velocity, that's Vix or Vxi. I get that by taking my initial velocity times cosine of the angle. So in this case, my initial velocity was 100 meters per second. Cosine of 30 degrees gives me 86.6 meters per second. That's the initial horizontal velocity of my projectile. My initial vertical velocity would be my initial velocity times sine of that angle. So 100 meters per second times the sine of 30 degrees gives me exactly 50 meters per second. So that's the initial vertical velocity of my projectile, or those two numbers. For part B, same initial information. Now they're asking us, after 2 seconds, how far has the object traveled in the horizontal direction. So horizontal, for my equation here that I'm using, this is my horizontal distance formula. So my final distance is equal to my initial distance plus my initial horizontal velocity times time. So in this case, I don't start anywhere. Like, they don't tell me I'm starting, this many meters off of the start line or anything like that. So if they don't tell you a specific starting position, you just assume it's 0. So in this case, it's really just that initial that initial horizontal velocity, which we found was 86.6 from part A, times the 2 seconds that they're telling us. So in 2 seconds, it's going to go 173.2 meters. And for part C, now they're asking us, how high is the object at this point? So at that 2 seconds that we just figured out, 170 whatever it was, meters away, how high is it at that spot? So at 2 seconds, this would be our equation that we were going to have to use for our final height. So our height at 2 seconds is going to be our initial height, which again, they don't tell us anything special, so we're just going to assume it's 0. Our initial vertical velocity we found was 50 meters per second. Time we know is 2, minus that thing that accounts for free fall, so minus 1/2 gt squared. So here, g we're going to use 9.8 meters per second squared. Time was 2 seconds. So here you'll have to do a little bit of order operation stuff. Square the 2 is 4 times 9.8 divided by 2, and you're subtracting that off of 100. Basically, so we get 80.4 meters. Now, I know I went through that kind of quickly, so feel free to pause the video, back it up, rewatch it a bunch of times if you need to. Definitely, you're going to want to take some time, either grab a note card or a Post-it or something, and go back to that slide that has your equations on it, because we've got those 5 equations that we deal with: my horizontal position, my vertical position, my vertical velocity, and then my 2 components as well. So we have those 5 different things that all of our problems are going to be based off of. So that's all I got for the video for right now. There's no homework to work on tonight or really for the weekend. Enjoy your 4-day weekend for your other classes. Use that time to get caught up on stuff. Or for those of you who have some stuff that are still missing for this class, make sure you guys are using the weekend. Tomorrow, Friday, for our work day. And obviously Saturday, Sunday, and Monday being Columbus Day, use that time as well to get stuff caught up, because next Friday, the 16th, is the end of quarter 1, and I need stuff submitted by the end of that day. So 11:59 p.m. is the cutoff for getting anything turned in if you still want it on the report card for quarter 1. Otherwise, it's not going on anything. So if you have questions, concerns, obviously feel free to reach out and let me know. Otherwise, have a great weekend, and I'll see you guys later.